really a great pleasure to be speaking with you today. Mathematics is one of my great loves, and I want to share it with you. And we're going to have 4 lessons together. And today I will give you an introduction to the lessons and then give you a lesson on numbers. And I know you all know a lot about numbers, but I hope I can add something that you may not know or give you a new insight onto what you do know. So I'll be sharing my screen. Okay, so here we have, this is a quote from Maharishi Mahesh Yogi about mathematics, and it really describes how I think about mathematics and how mathematicians work. The mathematician intellectually locates all the roots of knowledge in the functioning of his own consciousness and articulates them using the very precise symbolic language of mathematics. From these seed expressions of knowledge, all the different principles of mathematics are unfolded. So what I want you to understand here is that mathematics is rooted in your own consciousness, in your own awareness, in your own intellect. It's not something outside of yourself. And you have all the tools you need to do mathematics within yourself. And the 4 lessons we're going to do today, this week, numbers, set theory, modular arithmetic, and fractals. And I'll just show you what those are. So numbers, this is what we'll do today. We're going to be talking about numbers going from the natural numbers to the complex numbers. And this chart shows you how mathematics is something of the mind, it's something of the intellect, it's something of consciousness, and how it's related and supports physics. Physics deals with matter, and this is all the layers of physics. And one thing we see in physics and other sciences as well is that the deeper you go into mathematics, the more useful it is for the deeper levels of the discipline. So in classical physics, you just use the real numbers, but as you go deeper and deeper, you use more and more different kinds of numbers. So today we'll be talking about numbers, and then tomorrow we'll be talking about set theory. And set theory, you may have seen set theory before, but we'll be talking about infinite sets. And set theory really becomes interesting when we have infinitely many sets. And one of the examples we'll be using is something called Hilbert's Hotel that has infinitely many rooms. And this will actually be a theme throughout these 4 lessons, is that we're talking about infinity. And then on Wednesday, we'll be talking about clock arithmetic. Mathematicians call it modular arithmetic, but it's the arithmetic of a clock. If it's 10 o'clock, 4 hours later, it's 2 o'clock, 5 hours later, it's 3 o'clock. So it has a different arithmetic than the regular integers. And you may say, well, where's the theme of infinity in here? Because this only has 12 numbers. But it turns out we can have infinitely many different modular arithmetics, one for each number. So we have modular arithmetic for 12, 13, 14, like that. So we'll have infinitely many number systems. And then on Thursday, we'll be talking about the Mandelbrot set. And you may have seen this set somewhere, but we'll be talking about it in the context of fractals. And it has some very, very interesting properties. So that's what we'll be doing this week. And so we'll go look at numbers. And numbers, we'll talk about number systems. And we know that growth is natural to life. The nature of life is to grow. And what we've seen over history is that number systems have grown. In fact, the first number system is tallying. And you may have done this before, you're counting things. And so you go 1, 2, 3, 4, 5, 1, 2, 5, 6, 7, 8, 9, 10. And so, you know, you only have one symbol. It's just a line, vertical or diagonal. And, you know, that's tallying. That's a very, very simple number system. Now, another more elaborate system is called sign value. And sign here doesn't mean positive or negative. It means like a symbol or a sign. So in Roman numerals, this means 1, V means 5. And I'm writing out the words here so as not to complicate which symbol we're talking about. And X means 10. And if you want 20, you have to write 2 X's. And if you want 5, well, just the V and 3. So this is X, V, I is going to be 20 plus 5 plus 3. So that's 28. And what we have is, that we use today is the positional number system. But actually, I want to show you this, which I found online, which I thought was very interesting. This is the Sinhala numbers of Sri Lanka. These are ancient numbers used in Sri Lanka. And they are like somewhere between sign value and positional. So they're more advanced than the Roman numerals, but they're not yet base 10. And so we have the signs here. So this is the sign for 1, and this is the sign for 2. But we don't have a separate sign. You know, we have a 100 sign. Where's the 100 here? We have a 100 sign. But when we want to do 200, we don't do 2 of these the way the Roman numerals would do, but we say 2 times 100. So it has a multiplicative aspect. So it's this multiplicative aspect of this number system is really more advanced than the Roman system, which just said, if it's 200, let's see, here we have 200 like that, right here. So it's 200s. And so in Roman numerals, $200 would be CC, because C means 100. Okay, but we use the positional number system, or place value. So here we have a sign value, X is the value. Here the place is what gives us the value. So here X says that's 10, but here this can be 1 or 10 or 100. It depends on the place value. So now this 1 represents a 10, and now the 1 represents 100. And the beautiful thing about the positional number system is we can also do fractions. So if we do like this 1 corresponds to a 10th. So very, very useful number system. And this number system has given rise to the algorithms that we use, that you learned in grade school. Computers use base 2, and that's because in a computer, a switch or let's just say switch. A switch is either on or off. Okay, so that's why we use that in computers. And the beautiful thing about this positional system is numbers can go as high as we want. We can have 1 million, we can have 1 trillion, we can just go on and on and on. Whereas the Roman numerals, if you wanted to have 1 trillion, you would have to invent a new symbol, a new sign. And unary, forget it. You're not going to be able to do it at all. So the beautiful thing of our number system is that we can go on forever and ever. Now, what I'm going to do is we will look at the different number systems. And this is important because we're going to be using these. We're going to be using these tomorrow when we do set theory. And we'll be using the complex numbers on Thursday when we talk about the Mandelbrot set. So the natural numbers are the counting numbers. They go like this: 1, 2, 3, 4, 5. And using the positional number system, we can count to any arbitrary number. And so we say we can count to infinity. You know, I mean, that I'm saying that very loosely, but there's no bound to how we can count. So this is a beautiful thing with this number system, this positional number system. And when we say the natural numbers are the counting numbers, these are the numbers we count with. You know, we have 5 fingers. You know, we have 2 mangoes, like that. We can count things. Then we add on, and the theme here in this list is we keep adding on newer numbers. We add things on. And so here we're adding on negative numbers and 0. Okay, so counting, you know, a lot of times you say, well, I don't have anything. You don't even say I have 0 mangoes. You don't say that. You say, I just don't have any mangoes, or I have nothing. So these are the numbers you count with, and these are important. And negative numbers are important for bookkeeping, if you're in debt, for measurement, like temperature, 0. So these numbers are very, very important. Okay. And with the integers, we have the operations of addition, subtraction. Up here, we could do addition. With the natural numbers, we could do addition, but we couldn't do subtraction. Up here, we could do multiplication, and here we can do multiplication. With the integers alone, we can't yet do division. And so what we find is that this is like the nature of life is to grow. As we grow, we're capable of doing more and more. So now we can do subtraction. When we get to the rationals, now we can do division. Okay. So we have more operations. And then we'll talk about the real numbers and the complex numbers in a minute. But I want to talk a little bit about the rational numbers. And you're all familiar with these. You use them all the time. The word rational comes from the word ratio. So 2/3 is the ratio of 2 to 3. And the word, the letter Q is, okay, and natural numbers, that's easy. Z, mathematicians use Z to represent the integers because the German word for integers is Zahlen. And here, rationals, these are quotients. And then the reals and complex, they're easy to understand. Okay, so a rational number, 2/3 is a rational number. But we also have these decimal equivalents. And so what I want to do right now is I want to convert a rational number that's a ratio. I want to convert a ratio to a decimal. And I'm sure you all learned this in school. Now I'm going to do division the way that I learned it. And I know that in different countries, people do division differently. And you know, I would actually like you to do this on your paper while I'm doing it. And when I talked to Madhusha, I got the idea that your method was similar to the method that I've learned, but it may also be a little different. So 3 doesn't go into 20, it doesn't go into 2, but 3 goes into 20 around 6 times. And then I multiply. You can see what I'm doing. And then I subtract and I get 20 again. So I get 6 and I subtract and I get 20 again. And I can see a pattern. So the decimal is going to be 0.6666, okay? And there's different notations to indicate that that goes on forever. Sometimes people draw bars, some ... And I want to say something about what's going to happen here. And if this isn't how you do long division, bear with me. But what I did here was I multiplied 6 by 3 and I got 18. And then the remainder was 2. And then I knew I had to keep going. If the remainder had been 0, I would have stopped. So for example, let's do another division problem. Maybe I want to divide 30 by 5. So I say, okay, well, that's going to go in 6, and the remainder is 0. So I know I can stop, and I know I have an exact answer. So I can say exactly 30 divided by 5 is 6. If I didn't put these ... dots here, I would have to say something like 2/3 is approximately 0.67. Which, you know, we use a lot of times. Okay. But now the point I want to make here is that if I do a long division and I have a remainder, I know that I have to continue and the decimal is going to continue. But there's a special property that the remainder here has. This remainder has to be less than the divisor. This number at the bottom is called the divisor. When you, divisor. It's called the divisor when you're doing it this way, but in a fraction, it's called the denominator. You probably remember names like that from grade school. Anyway, the remainder has to be less than the divisor. And here it's 2, it's always 2, but you know, it could have been 1 or it could have been 0. It couldn't have been 3, it couldn't have been 4. What that means is, and this is a really, really important point, if you have an integer divided by an integer, and I'm going to do I'm not going to want to divide this out. It's just too much of a mess to do here in class. But if I divide this out, it's a fraction. I can do long division. And I can get remainders. And the remainder could be 0. Well, not in this case, obviously. The remainder could be 1. It could be 2. It could be 3. It could be 4. It could be all the way up to 31. And then I'd have to continue and continue and continue. But what would happen is it might take 32 steps. But eventually the denominator would repeat itself. I get something I had seen before. And when I got something I had seen before, I would go, okay, I'm doing the same thing over again. Okay. And in fact, this is called the pigeonhole principle. I know you're all interested in computer science. And this is something that is used a lot in computer science. And that is, you know, you have holes for the pigeons. You know, you have some pigeons, homing pigeons or whatever, pet pigeons. And let's see, I've got 1, 2, 3, 4, 5. If I have 5 pigeonholes, so I have 5 places to put pigeons. But if I have 6 pigeons, what happens? At least one of the holes is going to have 2 pigeons. Okay. So here, if I'm doing long division and I have remainders, I can keep having remainders going on forever. But they can't be, you know, the numbers are like the pigeonholes. Like the remainder could be 1 or 2 or 3 or 4 or 5 or all the way up to 30, 31. But sooner or later, they're going to repeat. I'm going to have to put a remainder in a hole that already has another remainder. So what I'm saying here is, if you have a rational number, a ratio, I'm going to do 1/7. I like that one. If you have a ratio and you want a decimal, then if you want a decimal, then it will repeat. Okay. So the rational numbers up above, I said the rational numbers were fractions, but they're also repeating or terminating decimals. Okay. So what I'd like you to do is start doing 7 divided by 1. I mean, 1 divided by 7. I can't believe I said that. 1, yeah, I said 1 divided by 7. So 7 goes into 1. Okay. So I'd like you to do this on your paper, and you'll probably be able to do it faster than I will. The reason I like this so much is because it illustrates something. It actually illustrates what I've just been telling you. Let's see, 7 goes in here too. And I'd like you to do whatever long division you learned in school. Okay. Now, what I like about this is I had to go through so many steps. So I got 1, 4, 2, 8, 5, 7. And then, okay, and here's the remainder. I had a remainder of 3, then a remainder of 2, then I had a remainder of 6, then 4, then 5. And finally, when I got back to the remainder of 1, I can say, okay, now I'm going to repeat. So I can just say, okay, then it's going to be 1, 4, 2, 8, 5, 7, like that. And sometimes we write a bar like that. That's a notation I've seen. Okay. Now I'm going to show you a trick. Suppose I have the decimal 323232 ... And I want to know the fraction. I want to know what fraction that gives me, or what fraction I would use to get 323232. I can't tell by looking at it. Now, some of you may be able to, or you might try a few numbers on your calculator and be lucky and get the right thing. It goes on infinitely. That's a problem. But one of the things that we do in mathematics is we handle the infinite as a totality. We just assume that we have the whole thing in our hand. So what I'm going to do is I'm going to say x is equal to 323232 ... forever. I'm not concerned that I don't know what it is or that I have to write it forever. I just call it x. And once I call it x, it's a totality and I can think about it. And this is one of the points I've been making, is that our awareness is really where mathematics happens. Consciousness is where mathematics happens. And our awareness is incredibly infinite. Here's an infinite decimal, and just like that, we understand what it is. No big deal for our awareness to comprehend infinity. Okay, and in fact, we can treat infinity just like it's a regular ordinary number. So what I'm going to do is I'm going to multiply both sides of this equation by 100. And I'm going to get 100x is, and 100 moves a decimal over 2 places. Okay. Okay, well, I mean, you could say, well, this is just as bad. It still goes on infinitely. Now it's just 100 times as worse. But what I can do is I can write, well, x is 0.323232. It goes on infinitely. We can handle infinity. We can handle it just by thinking about it. So what I'm going to do is I'm going to say, well, look, these are just numbers. I have my arithmetic operations. I can add, subtract, multiply, divide. I can divide both. I mean, well, I multiplied this. Now I can subtract. And this is why I did this, because look at this and look at this. They go in infinitely. Now I can't go 3 from 3 is 0, 2 from 2 is 0, 3 from 3 is 0, 2 from 2 is 0. I can't do that. I can't do step by step. But this is the thing about mathematics. When you see a pattern, and we'll see this over and over and over again, if you see a pattern, you can handle infinity. If you have a pattern, you can handle all possibilities. And of course, that's what you do when you create an algorithm in a computer program. You don't know what the input's going to be. You have to be able to handle all possible inputs. So you need a pattern, and a pattern is always abstract. It's a recognition of some uniformity, some structure. So we have a pattern here. This repeats. It's going to repeat infinitely. So when we do the subtraction, we go, okay, those are all going to cancel out. And we're going to get 99x is 32. And from there, we can get x is 32 over 99. Okay. And I'm not, and there's no way I would have guessed this from looking at this. After I had done some of these, I might start thinking, well, 32.3232 is going to be 32 over 99. But I didn't know that ahead of time. Okay. So I hope you did that along with me. What if X, oh, let's not use X, let's use, what if Y is 0.1111111? Can you do this on your paper right now? This one's a little easier. Oh, I got to put the dot, dot, dot. What's that going to be? Oh, okay. I've got 11 over 99 in the chat. I'm seeing this. Beautiful. That's the right answer. Okay. Actually, we can do a little bit better than this. I'm just going to go back and see what's happening. Somebody's asking, oh, good. We're getting 1/9. How did we get the 99? Because we had 100 and we took one away. So we're going to do a subtraction here. Okay. So I'm getting a 1 over 9 here. And this is you know, I said this was right, but now I'm saying 1 over 9 is right. Well, it's because these are equal. This is not in lowest terms. This is in lowest terms. You know, I'm not sure if you have the same terminology as I grew up with, but I think you know what I mean. If you have a fraction like this, you can divide the top by 11 and the bottom by 11 and get 1 over 9. Okay, so good. So we'll be looking at these numbers again tomorrow when we do set theory, but now I want to talk about the real number line. Okay, now this, and I don't want to spend too much time talking a bit about this because I'm really more interested in complex numbers, and I think you're all probably quite familiar with the real numbers. So if you, well, if you have a circle and the radius is 1, of course the diameter is 2, the circumference is 2 pi. Okay, so this is the circumference. And if you remember, pi, they always said, I don't know, sometimes it was 3.14. Oops, I got to do approximately. And there was a fraction, 22/7. I remember this was one of the first time, you know, in grade school, we did 22/7. In high school, we did 3.14. But later on in physics, you might do 3.14159, and then there's more and more decimals, and probably some of you learned it to more decimals than that. This is all I remember. This turns out to be non-repeating and non-terminating. And so it's not a fraction. You know, 22, that's why it's only approximately 22. It's not a fraction. And it's often called irrational. Okay, the irrationals are non-repeating and non-terminating. And remember I said we keep adding numbers up here? Well, we have the rationals, but we had to add more numbers because otherwise we wouldn't have pi, we wouldn't have square root of 2. Oh, somebody's got in the chat, somebody's got a lot more decimal digits than I had. So, so we have to add these numbers. Now, tomorrow we'll talk about how many there are. And of course, there's infinitely many, you know that. But it turns out there's really, really lots of infinitely many. Lots of infinitely many. So we'll see that tomorrow. And I think you're familiar with this, so I'm not going to spend much time on it. But now I'm going to talk about complex numbers. And maybe in the chat, some people could say, are you familiar with these or not so familiar? I have a feeling some people are familiar, and some people are not. But you know that we have, okay, somebody's familiar with these. Somebody missed some of the lesson, but it's being recorded, so we'll do that. You can look at the recording. So familiar, okay, and if you're not familiar, I don't expect you to say that you're not, okay, somebody said, somebody's willing to admit they're not familiar. Okay, well, let's go back up here and look at these number systems. When we got the integers, we got negative numbers. And they are very, very useful because then you can, you can take away 10 from 30 and you get minus 20. No, 10 from 30, you get 20. You can take 20 from 10 and get minus 10. You can do a lot more. And you can do a lot more measurements with that. Like you can have a thermometer. I live in a place where in the winter it gets below 0. I think you people are lucky it doesn't get below 0 unless you go on a mountaintop. But the complex numbers are an addition to the number system, the same way we added negative numbers, the same way we added fractions, real numbers. Now we're going to add more numbers. And somebody's saying they're imaginary numbers. And yeah, but here's the thing. When people say imaginary numbers, they think they're imaginary. And especially when we call the other numbers real. But the thing is, what you have in your imagination is as real as anything. Your imagination, your consciousness is huge. And so if you can imagine something, it's good enough. Okay, so one of the problems with the real numbers is no square roots of negative numbers of -1, -4, -9, -3 even. With the real numbers, we have square root of 4 is 2. Square root of 10 is 3 point something. Square root of 2, I think, is 1.414. I know some of those to a few decimal places, but But we don't have a square root for a negative number. So what mathematicians do is, well, we've been adding in numbers all along. We added in negatives, we added in 0, we added in fractions, we added in real numbers, we added square root of 2. Why not add in the square root of -1? It's just as legitimate as adding in all those other numbers. And of course, it's imaginary. All of them are imaginary because they're all abstract. They're all in our awareness. They're all in consciousness. And the reason I'm talking like this is I don't want you to be scared of these things. Sometimes people are afraid. They say, well, I don't know what's going on. We just call it I. Okay. Now, you know that if you take the square root of 2 and multiply it by itself, you get 2. And that's just how the square root of 2 behaves. So what happens with I? You can put this in the chat. It's real easy to do. What's I times I going to be? What's I times I going to be? -1. Okay. Samit got the first answer. Okay. Everybody else is telling me. Okay. Real numbers. Okay. Real numbers. Real numbers. You know what? And I'll be doing this in a minute. Did you ever do the real number line? These are the real numbers. And we use them to measure because we can measure the temperature, we can measure distances. Physics uses real numbers all the time. Okay, there's the number line. Okay, I'm going to talk a little bit more about the number line. So now, this is the complex numbers. A complex number looks like, and I do this double line here to make a bold. That's called blackboard bold, but it's whiteboard bold today. So we write a number like a plus bi. So we could have I, that's square root of -1. We could have 2 plus I, or we could have 1 plus 2i. These are all complex numbers. So complex, the word complex in English means as opposed to simple. And it doesn't mean hard. For some reason, we always think complex means hard. It just means it has lots of parts to it. So a complex number has 2 parts to it. It has a real part, and here I'm going to have to use the word imaginary. Sorry about that, but you all have good imagination, so it's not a problem. Now this one has no real part, and this one has no imaginary part. Okay. So complex numbers have 2 parts to them. Now we've started with the integers and we've built up to the complex numbers. And there's other numbers. There's quaternions, there's octonions, there's function space, there's all kinds of things. But we're going to stop here. And this is going to be good enough for the Mandelbrot set. There's 2 things more I want you to do. And I want you to understand how to do computations with complex numbers and how to represent them. So we use the ordinary old laws of arithmetic. I'm going to do a multiplication here. Oh, well, let's do an addition first. Let's add these first. Oops. Oops. Okay, so I want to do 2 plus I plus 1 plus 2i. So this is, you know how to add x plus y plus 3x plus 4y. You combine like terms. That's something you know. So we're going to combine like terms. So this is going to be 3 And these are like terms, so it's going to be 3 plus 3i. Okay. Now here, when we do multiplication, we have to use our distributive laws. So we're going to have 2 times 1. And I don't know how you learn this. Different people learn it different ways. The main thing is you have to multiply everything here by everything here. Some people do a different order, but I'm just going to do 2 times 1. 2 times 2i, so that's 4i. Distributive law. I times 1, so that's I. I times 2i. Well, this one is the only one that's tricky. 2 times I times I. But what's I times I? You already told me. That's -1. Oh, that's interesting. Those cancel out, don't they? So this is 2 times -1. So yeah, so all these people are putting 5i in there. Yeah, that's the right answer. Good, great. Okay, so that's how you multiply those numbers. Good, I'm seeing lots of 5i's. Okay, now one last thing. And if any of you have studied electrical engineering, and I'm sure some of you have, you're familiar with complex numbers because you use them a lot. Now, you know, I'm sure you all know this. If I give you numbers like this, you can plot them. You go over 2 and up 3. And this is called analytic geometry, or the Cartesian plane, after Descartes, who originated it. But you're very familiar with this. And you write y equals f of x, and you make a graph. And if you're not familiar with this, ask one of your friends, because this is something most people know about. Okay, now, imagine, okay, complex numbers were really called imaginary because people couldn't wrap their minds around them. But, you know, at the beginning, people couldn't understand square root of 2 either. It took a long time before they could understand square root of 2. But when a mathematician named Argand, he said, let's do a diagram. If I have 2 plus, let's do 2 plus I, what I'm going to do is I'm going to graph it. This is going to be my real axis, and this is going to be my imaginary axis. I'm going to go over 2, and this is I instead of 1, and I'm going to go up I, and I've got 2 plus I. And if I want to draw, I can even draw a little vector like that if I want. But I've got 2 plus I, and I've graphed it. Now we're going to see the value of this on Thursday when we do the Mandelbrot set. But the beauty of this is when we look at the plane, not as, this is sometimes called R2 or R cross R, because you've got an R here and an R here. If we look at the plane as the plane of the complex numbers, and this is just absolutely beautiful. Here, you could go over 2 up 3, you could draw a straight line, you could draw a parabola, you could do all these things. But complex numbers have arithmetic. They have addition, subtraction, multiplication, and even division. If we have time later, we might look at the division. But now what happens is we have arithmetic on the plane, and over here, each point was a pair of numbers. Now it's one number. And whenever you can unify things into one whole instead of 2 pieces, it's more powerful. So complex numbers, they have arithmetic, and they're very, very powerful. Okay, so we're going to have to end. It's been great. I was wondering how this would work with all these people online, but I can see that if you put something in the chat, it's easy for me to see it, and it helps me to understand what you're understanding. And I know that now I can ask you questions. So this is very, very helpful. So what we have done, just want to go back here. Okay. So we looked at the natural numbers. We looked at, well, okay, there's a distinction here between natural and whole, and I just I lumped them together. We looked at the integers. We looked at the rationals, and we saw that we could go from a fraction to a decimal. We could do that. We could go back and forth. The real numbers I didn't talk so much about, but we will talk more about those tomorrow. And the complex numbers, we saw that we had arithmetic for them. And we saw that we could plot them. So this is a 1 and this is an I. And so we have these numbers. And if you go on in mathematics, you're going to get more and more and more numbers. Okay, so thank you all very, very much. This has been a lot of fun, and I will see you tomorrow.